Sometimes, when we're trying to evaluate a limit, we come across various obstacles. And one of those possible obstacles is the combination of large and small terms. So let's see how we proceed with this. The terms large and small, taken to their extremities, would give you 0 and infinity. And we see here various combinations involving 0 and infinity that are not meaningful. 0 over 0, infinity over infinity, 0 times infinity, infinity minus infinity, 1 to the power infinity. All of those things on their own are not meaningful. But of course there can be an expression behind any of those limits there. When we have something involving any of those combinations, there are tools at our disposal. One possibility is to divide the top and bottom. If you have a quotient, divide the top and bottom by an expression, and then maybe you can make progress. So let's imagine two limits here. Limit as we're going to 0 and infinity of the same expression, 6x squared minus 20x over 2x squared plus 5x. Let's evaluate that at 0 and at infinity. So firstly, at 0. When we look here, if we just were to set x equal to 0, we'd have something of the form 0 over 0. More specifically, 0 minus 0 over 0 plus 0, but it's not something that we can work with. But if we divide both the top and the bottom by x, we choose x so that we get a finite term when we divide here, we get the same limit but applied to 6x minus 20 over 2x plus 5. And then, as we set x equal to 0, the 6x and the 2x, those tend to 0. We're left with minus 20 over 5. That is minus 4. And then the same expression as we let x tend to infinity, well, we can see top and bottom, both infinity plus or minus infinity. This is not a meaningful expression. But now let's take top and bottom and we'll divide by x squared. So rather than 6x squared minus 20x over 2x squared plus 5x, we get 6 minus 20 over x, we get 2 plus 5 over x, and then letting x become very large, the two fractions here, the 20 over x, the 5 over x, those become very small, so we're left here with 6 over 2, it gives us 3. We have evaluated the limit of this expression as x becomes close to 0 and as x becomes very large. And we can actually see, yes, we've got those limits, but let's just draw a graph of the situation and we can see that, yes, here is our function, 6x squared minus 20x divided by 2x squared plus 5x. As x tends to 0, it tends to minus 4. As x becomes larger and larger, it's tending to 3. So let's see a couple of limits here. It's the same expression, and we're going to 0, we're going to infinity. So here's our limit. Y is tending to 0, 12y cubed minus y squared over 4y cubed plus 3. Well, if we start off, and if we set y to be equal to 0, let's see what happens to the limit. So the limit becomes, well, on top, when y is 0, we'll have 0 minus 0. And on the bottom, 4 times 0 plus 3. 0 over 3, we get 0. So no problems for the limit as y approaches 0. We get 0 from the 0 over 3. For our limit as y becomes infinite, well, let's see what form we have. We'll have here 12y cubed, well, that will become infinite. Y squared will become infinite. And on the bottom, we'll have 4y cubed. That too is something that is infinite. So, this is not a meaningful expression. Adding the 3 on here will not make any difference. We need to try something different. And what we're going to do, let's divide top and bottom. We'll divide top and bottom by y cubed. So we get that our limit will be the limit as y tends to infinity. Divide by y cubed, we'll have 12 minus 1 over y when we divide by y cubed. And on the bottom, 4 plus 3 over y cubed. Remember, dividing top and bottom by y cubed will have our expression remaining the same. And now, as y tends to infinity, this minus 1 over y will become very small. 3 over y cubed will become very small. We get 12 over 4, which is equal to 3. So the limit going to 0 is equal to 0. The limit going to infinity is equal to 3. Let's see another example here. We have parameters a and b. We're going to see what happens as z becomes very large, as z goes to infinity, to az squared plus 1 over bz squared minus 3. And then investigate a little bit more fully the case where a is 6 and b is equal to 2. But firstly, we'll evaluate that limit in general. So let's look at our limit here. Z tends to infinity, az squared plus 1 over bz squared minus 3. We see if we were just to put in z becoming infinite, we'd have infinity over infinity. So this is of the form infinity over infinity. So just putting in z equals infinity, that's not going to help us. In fact, putting in z equals infinity to any expression is unlikely to be a great deal of use. But let's now divide top and bottom by z squared, the highest term on each. So we'll divide top and bottom by z squared. So we'll get that this is equal to the limit as z tends to infinity. We'll have a plus 1 over z squared over b minus 3 over z squared. And now, as z becomes very large, the 1 over z squared and the minus 3 over z squared become very small, and we're left with a over b. So the actual values of a and b are going to determine the limit. We're told to try a is equal to 6, b is equal to 2. For a is equal to 6, b is equal to 2, we would have that the limit, as z tends to infinity, of 8 plus 1 over z squared over b minus 3 over z squared, which of course is the same as our original limit, would be a over b, which is 6 over 2. It comes to 3. So let's bear in mind, we've established that the limit is 3, but let's just go back with some actual numbers. Let's see what happens to the expression az squared plus 1 over bz squared minus 3 as z becomes very large. We'll start some way from very large. The first value of z that we'll try will be equal to 1. So we will put in 6 times the value squared plus 1. We get 7. For bz squared minus 3, 2 times the value squared minus 3, we get minus 1. And then let's work out the ratio. This one over this one, we get minus 7. I thought we were heading for 3. This doesn't look much like it. What happens if we try z equal to 2? So the top line becomes 25. The bottom line becomes 5. We divide here, and we get 5. Well, no sign of our 3 coming into things yet. If we try z is equal to 5, what do we get? 151 over 47, we get 3.21 something. Z equals 10. .05. Well, we do seem to be approaching 100. 3.0005. 1,000. 3.00001. If we try 10,000, well, we can see our numerator and denominator, 6 times 10 to the minus 8, 6 times 10 to the 8, 2 times 10 to the 8, the ratio is equal to 3. Okay, if we allow more decimal places, you can see it's not quite 3, but put in 100,000, closer to 3, 1,000,000, and even to the increased accuracy we put in here, it's equal to 3. So our claim that the limit is equal to 3, well, we carried out algebraically the procedure. We found that the limit should be 3. We've put in various large numbers. And yes, we're finding from those numbers that the limit is equal to 3.